All right. Our project builds on the growing interest in quantum machine learning for fraud detection, while recent research explores a lot of unsupervised anomaly detection using quantum SVMs. Our work here tries to investigate supervised classification using VQCs or variational quantum classifiers. We wish to provide a comparative analysis between classical and quantum classification models, focusing on practical metrics like recall and F1 score to assess the viability of these quantum classifiers in realistic settings. And our work uses a subset of the same Kaggle data set and explores the impact of dimensionality reduction in quantum circuit encoding constraints in near-time devices. For businesses, this is becoming like a growing problem since financial institutions do face rising threats as technology becomes more sophisticated. So there is a growing demand for these advanced technologies that can enhance detection accuracy while operating efficiently under growing complex real world constraints. Our project aligns with the strategic imperative by exploring QML for fraud detection, a domain that combines the computational strengths of quantum systems with the predictive power of modern machine learning. Building on recent research into this type of anomaly detection, we apply supervised quantum classifiers to evaluate their viability on structured financial transaction data by comparing these models against classical counterparts using the metrics we talked about earlier. We can provide insight into QML's potential to uncover these types of fraud patterns.
Okay, so basically our data is anonymized using PCA, and our data contains transactions made by credit cards in September of 2013 by European cardholders. And this data set presents transactions that occurred in 2 days, where we have 492 frauds out of 200,084 807 transactions, which shows a balanced ratio between these classes. So what makes this data set particularly interesting is that um, our variables v1 to v28, um, we do not know what makes them original variables except for the three left untouched. Our goal is to research the inner workings of QML as we talked about before. So basically, our logic behind each method is that each of our data points in our feature space, which would be real to the power of 32, because we have 32 features, is mapped to the quantum state using a feature map function. And this feature map function is defined using Hadamard gates and a bunch of circuit encoding strategies. So we decided to end up using 5 qubits because 2 to the power of 5 entails 32 features, and this was most plausible on a Google Colab. And basically what we did here was we used a Hilbert space over complex numbers, and this allowed us to define angles and distances between our embedded quantum states, which is essential for our classification.
All right, so to visualize our data set before we go into QML, I mainly did three things. So first, wanted to map out time versus amount and compared to the class, since those were the only three untouched variables, just to show that, like at face value, there isn't much of a correlation in any way. So it's just mapped out every single time and transaction amount. As you can see, there's a lot of outliers, but most of it is like very low since most transactions aren't that expensive. And in the end, the two regression lines we get almost overlap each other, but this might also be because there's such limited fraud data. Below, we mapped out a histogram of all the distributions of each and every variable, just so you can get a sense of how each of these like peaks, since that could be very helpful in determining, fraud versus non-fraud. And lastly, we have a correlation matrix, which kind of shows what we expected, where a lot of these variables have very minimal correlation with each other, except on the edges, since those would be the variables that have the least variance. But that's just like a basic way of showing that a lot of these variables together don't really mean anything together. And we want to use, machine learning to actually find any patterns here, since At first glance, there really isn't much here. So to pre-process our data going into this, before we get into setting up these circuits, we wanted to undersample the majority class to create a balanced sample. So equal amount fraud, equal amount non-fraud, and then split the features and labels into the respective X and Y sets, and also use min-max scaler to basically normalize all the features so that they're all in a scale ranging from 0 to 1. And then we wanted to pad every variable in X to the nearest power of 2, since, as we talked about earlier, we want to map it to 2 to the 5, since this type of algorithm basically requires that the number of classical features be a power of 2, since that stems from just the structure of quantum states and the way that quantum circuits actually represent this data.
Okay, so going into our state preparation circuit, we perform a feature map, which basically presents our classical input vectors and turns them into a quantum state. And ansatz is basically our circuit architecture to set up for the rest of the circuits. And here we have a bunch of rotation gates, or rotation angles, I may say, for each of our qubits, and there are 5 qubits, as we said before. Um, we did a encoding class to make them as a binary classification problem. Um, and then this is just building our variational quantum classifier. We use a sampler and we define the feature map, our architecture, and our optimizer, as well as creating a function for tracking the training progress. And this is the result of our model. So we can see here that there is plot that shows our training progress over 150 iterations, where the cost function steadily decreases and eventually converges. And this just suggests that the model was successful in minimizing the objective function. After training, we evaluated the model's performance on a test set, and the classification report shows strong results. We see that our ROC AUC score is 0.86, which is relatively strong. However, we do see that there is 40 false negative cases, and this is visible in our confusion matrix over here.
Yeah, unfortunately, against the classical models, this actually did underperform. Going with the specifics, these all averaged about 0.92 and 0.91 as the average, which would suggest that, quantum machine learning does not operate as well. But perhaps this is as a result of the data, as we'll get to later, rather than as a result of the actual technology in play. So the way we tried to explain it using what we know, since at the end of the day, this is a very experimental form of machine learning, is that, you know, having 28 features after PCA is still quite small in comparison to a lot of like real world data that especially a lot of financial companies are most likely using. They probably have way more than 28, even though we can assume that before PCA that there were a lot more. Unfortunately, we will never know. And it seems that we might need a lot more in order for QML to show its potential, since quantum circuits are more sensitive to noise, which is often amplified in smaller data sets. When I say smaller, I mean variable wise. I don't believe that the actual amount of rows matters all too much, but unfortunately, we don't really have a way of knowing how many components are necessary to observe greater performance. But given what we could do, this is what we found.
Thank you.